Okay, thank you. Yeah, I'm happy to be here. It's my first time in Los Angeles, actually. And so far I like it, like really great campus. So I usually start with motivating a little bit what quantum phase estimation is. So like if you go to Wikipedia and check out the postulates of quantum mechanics, you see this thing that like observables are described by Hermitian matrices, and we can somehow observe the eigenvalues, and afterwards our system will be in the eigenstate. And when I was a student, that always confused me, but I kind of like took it as a postulate and worked with it. But over time, it made more sense. But on first glance, like what it doesn't really tell you is essentially, it more or less tells you something like this. Here's a system before observation. Then you can define an observable, like for example here, where's the ball, left or right? Then the matrix looks like this, a little bit constructed, and then there should be some way of detecting this. And after you're doing this, you will collapse into one of those eigenstates of your observable, and we will read out the corresponding eigenvalue here, left or right, for example. And in general, like I wouldn't know how to like take this postulate and really make measurements in a lab. Like it's not really my expertise. But at least if we have a quantum computer, for example, this essentially works. And the algorithm that does this is quantum phase estimation, where we have seen like a lot of details about this algorithm already yesterday from Dylan. And if you remember the first day, we saw a lot of resource estimates where this algorithm is actually used in order to observe, in this case, ground state energies of molecular systems. And we've seen it on the first day, like the resource estimates in the very beginning, they were quite unfeasible, but it's getting better and better. So like we're getting close to a point where we could actually use this in order to tackle ground state systems. But at the same time, there were also different approaches, like for example, the variational approach, which essentially uses that we can decompose our observable into a linear combination of smaller observables, and then couple this with a parameterized circuit, which gives us a representation of our quantum states. And the observable gives us just an instruction of what to measure. And what it leverages at the end of the day is then essentially that if you want an expectation value, then the large expectation value is the sum of the small expectation values, which doesn't hold for the eigenvalues themselves. So like in the beginning, it was often seen as an alternative to phase estimation, but it's not necessarily something that you have to put into two buckets. Like you can, of course, combine this. So for example, you could use this to optimize a circuit. Ideally, classically, like if you can do it classically, we can circumvent all the problems that usually come with these variational approaches. And so in the long term, we can have a two-step thing, like you use this to get a good initial state, and then you use it to prepare an initial state for this quantum phase estimation, and then ideally collapse into the state that you're looking for. And since your state register then collapses into the ground state, then at some point it's potentially also useful to think about more than energy. So like now you have prepared the ground state, and this is, for example, a good initialization if you're interested in dynamical properties, which is also then something which often like classical methods then struggle. Like we're good at like estimating energies, but if we want to do something else, the approximations might break down. So let's explore this a little bit, how we can initialize a good approximation for electronic structure ground states. And then there's essentially just two operations that we need. Like for most cases, we really get away with using only those two. Like one is the so-called pair correlator, and one is an orbital rotator, and both of them we have seen already in other talks, like under different names. So for example, this pair excitation operator that Arthur used yesterday is essentially the same thing as this operator here. So what it does, if we just look at a very simple model, like just assume you have two sites and two electrons, spin up, spin down, that you can place onto these sites. So like similar as in the first slide, like left and right. essentially, then what this pair correlator does, it treats electrons as quasi-particles and moves them around. It's like it moves the pair from left to right and can create linear combinations of this. So this is also in connection to what we learned from Arthur yesterday. So this is essentially operating in the seniority 0 subspace. Or you can also call this like a hardcore boson model, like if you prefer the quasi-particle aspect of it. And what the orbital rotator does is essentially it leaves the electronic configuration intact, but it changes the underlying representation. So in a sense, like it changes the orbitals or the sites in which you place these electrons. And with this, you can create like all types of circuits, and essentially you can interpret it then like you're always working like in a hardcore boson quasi-particle model, but what you're doing here is like you can change the model, like you can swap between different representations, and if you change the representation, like for example, what has been like a seniority 0 space in one representation is not necessarily a seniority 0 space in another representation. If you would glue this together, like let's just use these two operators and try to initialize like a good initial state. So for example, what we could do is we take 4 hydrogen atoms in a row, then we just place these two correlators here. I mean, we initialize here in some basis state that we have 4 electrons in the system. We optimize this variationally, and then we use it as an initial state for quantum phase estimation. So like what would happen if we use this in an atomic representation? This is essentially the result. Like this is the spectrum. Like these are all the eigenenergies of our Hamiltonian. And what you see on the y-axis is the probability to observe the ground state. So like it's very tiny. Like most of the probability is on some high-lying excited states. So this doesn't really work well. But you can do a tiny change. Like we can apply these orbital rotators here and just do a local rotation, and all of a sudden the picture changes drastically. It's like if we change the model, this approximation all of a sudden becomes very good, and we have roughly 90% probability to observe our ground state. Also, the spectrum shifted significantly to the low energy part. We can rotate even further, like into the optimal reference frame, and then this is essentially the best thing that we can get out of this initial approximation that we say everything is in this quasi-particle picture here. And now these type of circuits, we have the advantage that we can really tackle them classically. Like you don't need a quantum processor in order to optimize them and figure out the ideal angles on all of these tiny operations here. So to sketch this a little bit, this is the circuit that we had. And if we compile this into actual gates, like this would be like how it roughly looks on an ion trap, we can use the following strategy. Like first, we look just at this initial part here that works in this quasi-particle model. And this is essentially the only thing that we need, because everything else we can treat via orbital rotations in the Hamiltonian directly. And at this point, we can use the fact that we can separate this here, which also then holds true if the system becomes larger. We just get more parts. And then we get some equations where we can basically have to solve like a bunch of tiny fractions. But in the end, nothing scales exponentially here. So and at the same time, like these things here, since these are all orbital rotations, like we can also treat them classically by literally just rotating the orbitals in our Hamiltonian. And what you then need is like that's a technical thing. You need a fast way of evaluating reduced density matrices in order to couple these two things. But in principle, you can do this. Some prototype code that essentially implements this here in the Tequila library. It's just a few lines of code, and then you can just prototype it and essentially test it and like see how far you can get with this. And this is just some numerical benchmarks. Like if we do this, these are the wall times you would need like on a now like fairly old MacBook Air with an M2 processor. And this is how the full VQE optimization for, in this case, these are all hydrogen chains. So 80 qubits would be like 40 hydrogen atoms, and how to fully solve these VQEs classically. Of course, if you don't use any structural exploitations and just do state vector simulation, that's of course exponential. The green line is if we use this quasi-particle pictures, which cuts down our qubits in half. It's also exponential but shifted, and then the blue line is essentially if we keep decomposing everything. So around 20 qubits, that's usually where it's done faster. And if you couple this with orbital optimizers, you get essentially something like this, that circuit with 60 qubits you can do in roughly 1 minute. So this scales reasonably well on a classical computer, and we can now see like how far can we get with these type of approximations. Okay, so if we go back to our example here, like before we used these 4 hydrogen atoms here, like we had a spectrum like this, so behaved pretty decent. So like if we now try to scale this up to 6, 8, or 10 hydrogens in a line, or like up to 20 qubits, it behaves reasonably well. Like most of the probability is still on the ground state. It starts to dilute a little bit, but this is also what you would expect. Because essentially these circuits, they grow linear with basis size and constant with the number of electrons. And if you have something that is constant in size, but your test system increases linearly and it's designed in a way that correlation also increases, like you have to lose a little bit. So like the fidelity vanishes in a linear fashion. So it's something that you can definitely handle. If you want now to put the quantum back, basically, like this you can all treat classically. And so what do we need to do in order that it becomes unfeasible in a classical sense? And this is essentially if we do something like this. So if we rotate our orbitals, but then we do something else, and then we rotate the orbitals back. That's essentially something which all the classical methods usually not do. Like if you have the classical methods, you always have a fixed orbital frame. Like you choose one orbital frame at the end, you potentially optimize it, but you don't change it. Like you don't switch between different representations, and definitely not in like one evolution, so to say. So that also holds true for the standard unitary coupled cluster like unitary CCSD. And this is just because these single operators, which are these orbital rotations, they're not allowed to repeat with independent parameters. Like they always carry the same parameters. Like the interpretation there is more or less, they can be a correction to your current orbital picture, but they cannot change it, like that you're working in multiple ones at the same time.
Can I ask you a quick question? So
yeah, sure.
Can I think about this as being introducing more entanglement into the system? I'm trying to understand why it was classically simulable before in the first place. Like, because you have arbitrary angle of rotation, so I guess you have a lot of non-Clifford stuff going on, so that's not why. But it must have been not that entangled, I guess. That's why it's simulated.
It is in a way because, like before, it was a single orbital picture. So it means in the circuit picture, all the orbital rotators are at the tail. And if they're at the tail, you can absorb them into the Hamiltonian. But if they're in the middle, you can't. And before, they were never in the middle, essentially. And
so the circuit up until the very end had low entanglement, is what you're saying, or low.
Yeah, because you could absorb those into the Hamiltonian, and then you had something that was designed to be separable. So like it's only entanglement can then only happen between these individual pairs. Like if you increase the basis, you can get fairly entangled things, but you still have like a cluster. Like you can still deal with it. Like entanglement can become quite high actually, but it's so structured that it's not a deal breaker at this point. Yeah.
Could you explain any intuition about why you put this specific entangling at this specific position? Is there any physical reasoning about it, or you just want to increase entanglement?
So in general, it's like as soon as you do this, you can basically not exploit the structure anymore. But what you can do, of course, also is like now this gives you a way of interpreting the circuit here. Like like here you rotate into a different model basically, then you correlate within that model, and then you rotate back into the old model. And if you look at a specific molecule, like we have 1 or 2 examples for this later, you can basically, with a little bit of chemical intuition, guess on how these orbital bases look like in which you need to rotate.
Sorry, I have a question. This is very in the weeds about chemical methods in chemistry, so you can say no, or you can spend maybe 1 minute on it. There's sort of non-orthogonal configuration interaction wave functions where you sort of do a sum of different orbital rotations on determinants. So that's sort of not a product like this, but that's one. And then there's these like neural backflow wave functions, which also do sort of configuration dependent orbital rotations that sort of allow you to access something that doesn't seem to be precisely this, but it has a similar spirit or flavor. I don't know what I'm asking. I'm just
no, that's definitely true. Like NOCI, for example, does exactly this, but it does linear combinations. Yeah, like as you said, like it's not a product, but a linear combination. Same as like multi-configurational valence bond, for example, which is also operating in different orbital bases, but it makes a linear combination out of them. So like those are actually like I think those are the classical methods that come closest to it in a sense that they also, in a way, break this one orbital representation setting. Yeah. Yeah.
Yeah. So I just want to articulate what I think you're saying, and I want you to tell me if I'm wrong, if that's okay.
Yeah, sure.
So I think what I'm hearing is like up until this point, like you wouldn't need a quantum computer, you don't need any kind of fancy anything. You can do this classically, but it's also not general because like not everything is going to be decomposable and separable in the way that you described up until this slide. And so this is like, okay, well, realistically, this might be something that you need to be able to do. You might need to be able to do these interspersed rotations and correlations. And so at this point is when you're going to start to dig into like, okay, here's why we need actual quantum computers to solve this kind of thing. Is that?
Yeah, I think that sums it up quite nicely. Like originally, like the idea came from being able to interpret why some Ansätze fail for some systems and some don't, like to being able like to interpret what's actually happening here. But at the same time, it was also a nice way of illustrating like what's really different in this circuit-based approaches if you compare this, for example, to classical coupled cluster.
Okay, and then one follow-on question, which is, I think the answer is yes, but if you can color it more than yes, like, are there specific sort of applications that you can think of that require this kind of structure that depart the sort of separability that you described before?
Yes, next slide.
Hey, all right.
I can give you one example. Like if we go back to these hydrogen chains, for example, we have seen this before. So we could now start doing this. Like this is the separable model here. Like this is classically representable. And I called this G1 because it's essentially like it's a connectivity graph. Like you can view this as these two atoms are connected, these two are connected, these and these. But if the distance is the same, you could also say those are connected. And this is essentially what the second graph does. Or in chemical language, like it's like two resonance structures that you're looking at. And these are the two lines. Like this is the G1 and this is the G2. Like this is essentially like the correlation that you're losing, because the larger you grow this chain, the more of these resonance structures you have, and the more important like also the second one becomes. So like at the very end, like at H2, it's essentially just the first one because there can only be one connection. The comparison here is a little bit with a standard unitary coupled cluster method that was explicitly designed for these circuits, and which is also very popular. And I chose this because it uses the same operators, like this UPCCGSD uses also just these pair correlators and these orbital rotators, but it doesn't use this chemical insight in a sense. So you see, if you do this, and then if you increase the layering, which also gives you quite deep circuits, you have really struggle of converging. Like, in principle, this ansatz here is able to represent the system accurately, but in practice, you don't find the optimum. That's basically the issue. While here we have something that works very systematic and systematically improves. And it also improves in a way as you would expect it, or like the most that you can hope for, because if you look at the circuit depth, like all of these are essentially constant. Like we just increasing it, and then it's again like it's the same thing. Like you have something, correlation increases linearly, circuit depth is constant. Like you have to lose linearly if you increase the system size. So conjecture would be that you need to pick up a linear number of resonance structures in order to deal with it. Although, like to be honest here, convergence becomes tougher the more you put in. Like you see this here, like it stops here because I ran out of compute time at this point. It was on a laptop though, like I think I could do better here, but it definitely becomes harder to converge. Yeah.
So is it a linear trade-off between precision and time, or is it worse than linear, or?
I can't tell at this point. Haven't been that extensive, but I think like it becomes more and more complicated, and the more structures you put in and the deeper the circuit is, the less intuition, at least I have, on how to initialize these orbital rotators. Like in the beginning, it's relatively easy, but then it's selecting like the structures. Like here, it's kind of clear that this is the leading structure and this is the second. But then afterwards, like you have a lot of choices. Like it grows factorially. Like you don't want to pick up all of them. And for this, I don't have an answer at this point. Yeah. Yeah.
Do you kind of use what you know from one layer that you've already optimized for, and then use that as a starting point whenever you increase layers, or do you start from scratch every time?
I tried both. For the first two, they converge like really nicely, and it doesn't really matter. Like both strategies work. Like you're there in 10 to 20 iterations. More than two, it becomes difficult, and I wouldn't say it's something that's currently applicable. Like sometimes one strategy works better, sometimes the other. But I think it's really just because I ran out of ideas on how to initialize this in a way that it converges. Yeah.
So in this system with the hydrogen chain, if I'm understanding correctly, because of like the symmetry of the molecule, do you see any like patterns in the like parameters themselves, like having any like correlations or?
Oh yeah. You have this like essentially like these are the same as these. These are the same.
So you already posed those constraints when you optimized?
I think I didn't in these calculations, but it didn't make a difference because they're all initialized in the same way. And so they naturally always, like the symmetry is there, like they can't escape it. Like it's not randomly initialized, yeah. There you would have issues actually, yeah. Okay. So that was a little bit the separation, like how far can we go classically so far with these type of methods, and then what is actually needed if you want to go one step further. I want to just present some ideas that we had for real molecules, which is one of these things that if you do collaborations, like chemists like to do real molecules and not hydrogen systems, and it's always as Arthur said, like it's similar as with the competition, it's a nice driving factor because it forces you to actually look at these things. So one idea that we once had when we needed to simulate like a full benzene molecule was to use this chemical intuition in a way like to look at these connectivity graphs and separate it also in a product form. So in this case, like we take the sigma framework and the pi framework, because the pi framework is clearly not, it can't be described by a single resonance structure. Like it's the poster child of these type of patterns. And so, but at least intuitively, like the sigma framework should be representable with these separable states. So like everything classically, everything in this quasi-particle model, and like everything decomposable, while this thing isn't. Like, yeah, you can't do it in the quasi-particle model. You need fermionic encoding because there are like two different orbital bases in which you need to rotate. One then looks locally like this, one locally like this. And in order like to do this like in one giant circuit, you need something like a hybrid encoding, basically, that some parts are fermionic and some parts are hardcore bosonic. And this is essentially what Javi did. And then we tried to see what actually happens if we try to compute a chemical property. Like, I'm doing something simpler than benzene now because it doesn't take so long computationally. So like one of the simplest models would be, it's essentially very similar to these H4s. So like just now we have like a pi system with 4 electrons, but it's embedded in a sigma framework, like for example in this butadiene here. And we look at the rotation energy if you rotate around this bond, like what's the barrier that this molecule has to overcome. And this essentially looks like this. So like first, this is like the reference calculation, which I think we did CCSD parenthesis T and DMRG at the same time, just to make sure that this is probably accurate in the basis that we've chosen. And if we now use the same strategy as before, but we just look at the pi system, so like we treat this in an active space, so in a sense, sigma framework is all on Hartree-Fock level. This is essentially what's happening. Like if we use this classically simulatable, what's it called, like separable ansatz here, we got energies that look like this. Like it's not terribly wrong, but it's also not great. And if we include the second resonance structure, which would be like the bond is here, and here we have like, here we are open, then it looks smoother, but it somehow it goes away from the reference, like it moves in the wrong direction. If we now take this active space and just do an exact diagonalization on this, we get this lines, like it moves even further away from the actual reference energy, which essentially means that it's not a good approximation, like to just look at the pi system and freeze the rest. So if we now take this sigma framework into account as this product ansatz and use this separable representation here, so like this is embedded then in a giant circuit in this hybrid encoding, we get the following picture. Like this is again, if we treat the pi system only separable, like this is terrible. It's not very great, like fake minimum here, but at least it's not completely off. But if we now treat the pi system to full extent, that already looks much better and it goes in the right direction. And if we check the model limits, so like essentially do a full diagonalization on this model or like expand the circuit with more correlation, we see that we more or less hit the reference energy exactly. So it means the approximation works quite well here. For the project back then, it was actually that the approximation worked too well because we wanted like to improve upon the approximation. So like this was not a good test system, unfortunately, but that's how it goes. And here's like just some ballpark numbers, like how far you can go with this. So these things are roughly like it takes you 5 minutes, like on a laptop. To optimize this, well, if you go larger, so like for example here with this naphthalene, or I forgot what this molecule here is called, which has like a smaller pi system but a quite extensive sigma framework, that takes currently 1 to 2 days. Although what's kind of important is that this is not high performance computing. So like this is all done, for example, in this Tequila software package, which is very flexible. Like it can do a lot of things which are not necessary here. Yeah.
Yeah, I want to sort of understand, it's not HPC, but then it's this Tequila package on your laptop or something, so it's also not quantum computing, I guess. I'm guessing you're not running on a quantum device or they'd be a lot noisier. So when you say 80 to an 86 electron sigma system, full circuit optimization in 1 to 2 days, are you simulating a large quantum computer somewhere? Like how are you optimizing the parameters?
It does essentially just like you can construct the circuit, then you do the orbital optimization, like you subtract from it, and then you use the fact that everything separates and use these hybrid encodings. And then at the end of the day, you have to simulate a lot of small expectation values. And the software is just not made to do this in a fast way, like no parallelization and everything in Python. This is essentially what's costing us this 1 to 2 days.
But at that limit, I would call this a quantum-inspired algorithm, because you're not utilizing enough entanglement structure to actually need to go to a quantum computer to do that, because you're doing it classically.
Yeah, the goal is basically to optimize these circuits classically, like to circumvent all the VQE problems that we have, like no measurement problem at this point, no noise problem, and also not an issue with, for example, that gradients are expensive and that you need a lot of shots in order to get an accurate gradient. So like the goal would be here, like you do all of this classically, and this is how far you can get classically, and then you have something that initializes you a decent approximation of your ground state on a quantum processor. But at this point, you probably don't want to continue the VQE route, but rather go phase estimation, or if you're able to approximate the ground state well, maybe also something dynamically, yeah.
Can I analogize this to like match gates and like match gate simulations?
These orbital rotations are essentially match gates, yeah. It's different name for it, yeah. On a way, you can compile them into match gates. Okay. Then something I originally didn't want to talk about, but I think it connects well to the themes that we had already, is if we, instead of going down the VQE route, we look at effective basis, so like making our wave function as a linear combination, where we have seen some methods from Matthew 2 days ago and from Arthur yesterday. And you can take the same design principle that we use for the circuits now, that we use these resonance structures, and say instead of like a product, we can make a linear combination. But what you get then is essentially multi-configurational valence bound theory, like which is a classical theory. Yeah.
I'm realizing that maybe you're changing topics, so I could ask about the previous part before we get launched into this. Is that okay?
Yeah, sure.
So the basic idea is that you want to have a classical approach to optimize a state that's close enough to then propose an initial state for, say, phase estimation in the previous part of your talk. Yeah. And so the kind of state that produces, that optimizes classically, do you know if it's low depth to produce that then in a quantum? If you're going to then that's the start of a fault-tolerant quantum computer, is it like low T depth, or do you have any idea if that's actually easy to then make as your
Yeah, it's extremely low depth actually. If we had it before, like with these hydrogen chains, for example, the depth is more or less 4 or 5.
If you have arbitrary angle rotation, but if you have like a fault-tolerant quantum computer, so you have Clifford plus T.
Oh yeah, so like depth is 4 or 5, and then it's all Cliffords except for some single qubit rotations, and then you have essentially for each basis state, for each basis orbital, you get 1 rotation. It's like that's linear in the number of rotations that you need. Like those you need to decompose into T's. But I think this is as cheap as it gets. Like I think you can't make it much cheaper, yeah.
So if like a tensor network, you would say it's cheaper than if you optimize a tensor network state and use that as the quantum physics. Or you don't know, maybe you have...
I'm pretty sure it should be cheaper, yeah. Because it's basically designed to be hardware efficient. Like you can't optimize any of the gates away anymore. Like it's super compact at the end of the day. Like it's really, it's just a few C-naughts. The depth is tiny, and you have a minimal number of rotations in the end. But it's of course also a very simple model. Yeah.
This is in the theme, but a little more generic question. One thing that I find very hard when designing quantum algorithms, and especially heuristic-y like things like this, is I can't test them. I'm writing heuristic programs for devices that don't exist. And so we do our best with extrapolations and some models and things. I guess I want to get your insight, because I think it's part of bridging the gap between NISQ, where we can kind of simulate 30 qubits if we wanted to ask what the performance is before going on to a real device, and fault-tolerant quantum computing, which is sort of much farther away, where that won't be possible. And you have a sort of interesting idea here that is a little bit there, but how would I test how good your system is at going to the next step? Like what, I don't know how to do it, except maybe sparse wave function simulators or MPS wave function, MPS-based simulators, which maybe gets you a little bit further, but not that much farther. So maybe I just want a comment of how you would imagine trying to test this at the next step, presuming.
What do you mean with next step?
So someone gave you a quantum computer with 100 logical qubits and 1,000,000 gates. And this is like step one. You've sort of designed a step one, an efficient classical emulation. And now step two would be put that on a 100 logical qubit with a 1,000,000 gate machine and now get an energy that's better than the thing you did classically and cure cancer or whatever end goal you want to do. Right? That's where we want to get, but I don't know how to test whether my algorithm is going to be good on that device because I don't have that device to test on. So it's heuristic. You're designing heuristic methods without an ability to judge their performance on a 100 logical qubit 1,000,000 gate system.
So since the circuits at the end are like really tiny, my working hypothesis is usually like if you can't run those circuits, then you can't also do much more at the end of the day. Like if I can run 1,000,000 gates, I should be able to run a circuit of depth 4, no matter what's inside, basically, even if everything is parameterized in there. So I think it's safe to assume like that this should be possible. Like this initializes me the state as it's supposed to be.
Maybe I'll ask my question subtly differently. I want to know what the benefit of your state loading technique is against my state loading technique for quantum phase estimation or imaginary time evolution or Krylov-based something. Both of our methods are heuristic. And so at the end of the day, we can sort of fight and argue about parameter counts and resource estimates and this and that, and that's what I do in my papers at least. But at the end of the day, the proof is in the pudding. Like I'm going to go run QPE gives us a certificate, but maybe some early fault-tolerant algorithm doesn't. So is there any way for us as a community to like benchmark our methods at the next step? But the next step, this sort of existed. This device doesn't exist, so it's really hard.
Yeah. I mean, I think one need to do it like device independently, basically. Like what's the cost? Like how many gates, how many parameters do you need in order to get a specific fidelity for some benchmark systems? Like for example, these hydrogen chains or like conjugated pi systems, but the full molecule. That just gives you a number back. Yeah, that would be it. I think this is just a comparison then, like how deep is the circuit, because then you can also estimate a runtime, like how much time does it actually cost you to initialize.
I think that misses how accurate the resulting circuit is. And that accuracy number is what I worry about because I can't estimate that a priori for many variational-like algorithms.
What do you mean with accuracy?
Yeah, so I run my early fault-tolerant quantum algorithm, which is imaginary time evolution on top of a trim CI loaded wave function, or on top of your wave function here. After 3 steps, it will have some energy, and that energy will be different from the true ground state energy by some epsilon. And I don't know whether that difference is small or large because I would sort of have to run it and measure to get the answer.
Yeah, that's tough. Yeah, I don't know. Like, I guess if you don't have the machines to play with, it's hard to really test it. Like, yeah, you can just do estimates, in a way. Go. Yeah. Yeah. Let's go this direction. this order.
Okay, it was a follow-on to this discussion, which is, couldn't you just pick like a value that's been experimentally validated that's otherwise very difficult to calculate and just like see how this does?
Except I don't have I'm working in the regime where I don't have a 100 logical qubit million gate device to run on.
Oh, you're saying, and you would need it in order to do it at all.
Right. And that's why we have great theory of QPE, which says this will give you the answer with this accuracy at this gate count, right? Because we don't want to be in this realm of heuristics. But I'm a believer in heuristics. I'm a believer in subspace expansions and these things. And I really want to test things, and I can't. And I'm always asking people how. And the answer might be you can't. I don't know. But
Okay.
that's...
Understood. Thanks.
I have kind of two questions. One's kind of related to this discussion. Well, if we talk about heuristic and state preparation, we always know like in which case this algorithm is gonna fail. Like what's the failure mode for this specific algorithm? And then another question is like, since you have very low depth circuits with a bunch of like most of them are Clifford. Have you ever tried to use this kind of Clifford plus tensor network simulator and see like whether you can just make the whole algorithm possibly?
Oh yeah, I mean, that's essentially what I was doing, but not with these specific type of simulators, but like by essentially just exploiting the structure, yeah.
How about when does this algorithm gonna fail? Do you have like, I kind of imagine if you have like strongly correlated system, that would be very hard to come up with the circuits or like do the optimization.
I mean, what you can always do the approximation, and then you basically get the best result within that approximation for your system. But it's not designed like to solve systems to 100%. Like it's just designed to give you a decent approximation in the end. And there have to exist like systems where it fails completely.
Yeah. But do you have like a characterization of like which class of problem this algorithm gonna fail?
I think from what we've tested empirically, usually like everything organic is fine. I've never touched metals. I think it can become difficult with metals. Like if a lot of electrons are cramped together, you don't. It's hard to make these valence bond pictures, basically.
Have you tried it on a system with a triple bond?
Yeah, for example, nitrogen. It's like first level is fine.
That doesn't have a resonance structure. You have an organic molecule where you have a triple bond, but there is a resonance structure possible.
Yeah, it's then usually like triple bonds are a bit tough. You can approximate them still well on this first level, like classically, but then improving on it in this valence bond picture is not so easy. I'm gonna skip the last part due to time issues. It was basically just in general, I think like these valence bond ideas are quite interesting, and I think they have been abandoned because you have very compressed states, but if you need the states to talk to each other, that's essentially the thing. These things are hard in these valence bond methods, but on quantum computers, they're not necessarily hard. Like they're not designed for NISQ approaches, but in principle, it's not exponential in order to rotate into these different frames. So a lot of these ideas might be like, in a sense, like designed for quantum computation, but they just came too early. So this is the last part I'm gonna skip, which is essentially like optimizing the basis, because I promised this holistic picture in the title, but we're not gonna go into the details. Like, sorry for like being fast here. But I prefer it this way, like to have a discussion. I mean, this is the very last picture. We started with this in the beginning. Now, if you think about, you use some fancy numerical methods in order to optimize the basis. So like the three-dimensional functions that you need in order to get your discretized model. It's like you're not operating on a static basis. You're free to change them as much as you want. And if you, for example, do this, this is essentially what happens. Like your spectrum shifts to the left. This is essentially, you get a better model of your molecule in your discretized Hamiltonian. And at the same time, you also have suppression here. Like you get you're even like more targeted on the ground state in the end because you're doing a full optimization. But let's not go into the numerical details of this. Summary we can skip. With this, I'm at the end of the talk. If you ever feel the need to eat like some Weißwurst and drink some beer in the morning, give me a call and you're welcome to visit in Augsburg. Since the talk is recorded, I need to emphasize that the beer is, of course, non-alcoholic.
Oh.